Good morning, ladies and gentlemen. Today I'm going to be taking the second class on my aircraft performance. I request you to watch till the end of the video because during the session I'm going to be answering some of the common questions which comes onto the examination. Some of the common questions are: what are the range of a V2 with respect to the stalling speed? What is the range of a V1 again with respect to the VR? What will happen to the V2 if the CG is forward? And maximum speed of VLOF is governed by can V1 be lower than the V engine failure? And maximum speed of a V1 will be governed by what are the other factors? So first of all, as we have talked about the stalling speed, we will see what exactly is the stalling speed and its effect on the takeoff speeds. When we talk about the stalling speed, what exactly is the stall? In the first diagram where my mouse is hovering around, okay, it is for the normal flight where the free stream is divided into two parts. On the upper side and the lower side, as a speed over the upper side of the aerofoil increases and thereby reducing the pressure above the aerofoil. That is how we get the lift, which sustains or which is equal to the weight of the aircraft when the aircraft is on a straight and a level flight. But as we keep increasing the angle of attack, okay, with the power reduced to the idle thrust and try to maintain the same level, okay, we require more lift, or we require the same amount of lift, for which we need to slowly increase the angle of attack. Okay, while doing so, the airflow over the upper part of the wing towards the trailing edge will start separating from the boundary. So this is the trailing edge separation. As we keep on increasing the angle of attack in order to maintain the lift which is equivalent to the weight, there will be one particular angle of attack, okay, which will give me the maximum CL max, maximum lift. Okay, that particular speed or that particular angle is known as a critical angle of attack, and that particular speed, if we reduce further, then the aircraft will no longer be able to sustain the weight of the aircraft. So therefore the aircraft will suddenly lose the height. This phenomenon is known as the stall. So if we see that the speed at the critical angle of attack below which an aircraft for a given configuration and the weight can no longer be able to maintain the straight and level flight, that particular speed is defined as the stalling speed, and that particular angle, okay, is known as a critical angle. Let's have a look at further in this diagram. This particular graph, on the y-axis is the CL max, and on the x-axis we have got two lines. Okay, the first line, which is black in color, is the angle of attack, which is increasing from left to the right. As we increase the angle of attack, okay, the aircraft will slowly lose the speed, that is the CAS is losing or decreasing from right to the left. After the engine thrust or the power has been put onto the flight idle, or in some cases into the ground idle, the aircraft will require more angle of attack. The aircraft will lose the speed of the aircraft because of the drag. As the aircraft is losing the speed, the lift produced by the aerofoil is reducing. In order to maintain the lift, what a pilot needs to do is to increase the angle of attack so that the lift is still able to sustain or maintain is equivalent to the weight of the aircraft. A particular stage will come as we keep increasing the angle of attack, the CL will increase and it will reach a certain stage, okay, where it is maximum. This place is known as on the graph is known as this is the CL max, wherein at CL max the lift is still equivalent to the weight of the aircraft. Therefore the aircraft will still be able to maintain the straight and the level flight. If we talk about the load factor which is lift upon weight, when the lift is equal to the weight, will be equal to the 1. So this particular speed at which the lift is equal to the weight of the aircraft, where the load factor becomes 1, that particular speed is known as the VS1G. Beyond this, if I increase the angle of attack further, the aircraft will suddenly lose the lift and will no longer be able to sustain the weight of the aircraft. Therefore, at a particular speed, the aircraft will stall or start losing the height. During this period, the aircraft will experience lesser controllability from the control surfaces. The particular speed at which the aircraft stalls or start losing the height is known as the stalling speed, which is known as the conventional stall. But in modern aircrafts like fly-by-wire aircraft, the stalling of the aircraft is protected by the system. In this case, since the aircraft is not going to be stalling, I need to define a particular speed, which is the reference speed. So reference stall speed, which is written in the green font. So this reference stall speed can be determined by the manufacturer of the aircraft, but this stalling speed, VSR, can never be below load factor 1. But in some cases, or in most of the cases, many manufacturers define this reference speed at that particular speed where the aircraft is still able to maintain the level flight, that is where the lift is equal to weight when the load factor becomes 1. So therefore, the names come that V reference, that is the reference stall speed, where the load factor is equal to 1 is known as the V stalling at 1G speed. So this is an accepted stalling speed for the modern aircraft, which are protected from the stalling. So if we try to correlate between the conventional stalling speed and the VS1G, since the VS1G is higher than that of the stalling speed, the relationship becomes V stalling is equal to 0.94 times of my VS1G. So from now onward, if I mention the stalling speed, I will be referring to the VS1G only. So during the takeoff, as we have discussed earlier, that we have got two options in the event of an engine failure. The first option is to reject the takeoff and stop by the end of the acceleration stop distance available, and the second option is to continue the takeoff and reach V2 by 35 feet. Now I'll be talking about continuation of the takeoff. If I have to continue the takeoff with an engine failure, I have to reach the V2 by 35 feet. That is, when can I declare the aircraft safely airborne? I can declare that the aircraft is safely airborne only when the aircraft reaches V2 by 35 feet. That is why the name of this speed, or V2, is also given as the takeoff safety speed, and which is defined as the CAS that must be attained by 35 feet height during takeoff, and which ensures a 15 degrees of angle of bank and the maneuver capability and the specified safety margin in relation to the stall and the control of the aircraft. So he is telling you to have a safety margin with respect to the stall. So therefore I need to give a V2 which is slightly higher than the V stalling. So if I talk about the VS1G, my minimum V2 has to be at least 1.13 times of VS1G. If you are flying an aircraft which is not referring to the VS1G, if you refer to as the V stalling speed conventional, then it will be the minimum V2 should be at least 1.2 times of your V stalling or VS. And this particular V2 can be increased up to 1.25, 1.35, 1.4 depending upon the design of the aircraft. Why do we have to adopt to increasing the V2? I will be discussing on my next class in my optimization of the takeoff weight. Thereafter, the second criteria for V2 is to have some controllability in there. After getting an airborne, if a flock of birds come in front of me, I should be able to avoid or carry out a maneuver to escape my aircraft from that. So I need to be able to have some controllability in the air. That particular speed is we have discussed in the previous class. If you have not attended, kindly look in my previous class. That particular speed is known as the VMCA, that is velocity minimum control in the air. So therefore my V2 speed has to be higher than the VMCA or equal to the VMCA, but by regulators my V2 minimum should be at least higher than the VMCA by 1.1 times. So 1.1 times VMCA. As also we have discussed in my previous class, the VMCA is determined for the maximum takeoff thrust, okay, in certain aircraft, and for the derated takeoff thrust also for some of the aircraft which are using the derated. Okay, so this particular VMCA is determined for the takeoff thrust or the takeoff power if you are flying in a turboprop aircraft. So, and also we have mentioned that it is determined for the maximum takeoff weight of the aircraft, considering the aircraft is trimmed for the takeoff and the worst CG. Okay. Therefore, by and large, for a given configuration at a given pressure altitude, the value of the VMCA will not change. So therefore, my V2 with respect to the VMCA for a particular pressure altitude and the config will remain the same. That is the V2 minimum. So my V2 will therefore depend primarily on the V stalling speed. So let us have a look at the functions of the V2. That means to say that which all decides the minimum V2. As we have seen that the V2 depends upon the stalling speed. The factors, okay, on which the stalling speed depends are the weight of the aircraft. If the weight is higher, the stalling speed will be higher. So therefore my V2 will be higher. And if we talk about the configuration, for a lesser configuration, as we all know that my speeds have to be higher. Okay, so therefore for a lesser configuration my V2 will be higher. And again, how will it depend on the CG of the aircraft? So when we talk about the CG of the aircraft, okay, kindly follow my mouse. This is an aircraft, okay, or the aeroplane where I have got the wings and the tail plane, and at the center of pressure X. At in this particular diagram, with this is represented by the green arrow line where the CP is written. This is the center of pressure. Normally, in most of the aircraft, the center of gravity will be slightly ahead of the center of pressure. So therefore, there will be always a slight nose down tendency in the aircraft. But as long as you are having all the engines operative, when your engines are operational, this particular downward couple which is there existing because of the CG will be compensated by the thrust vector of the aircraft. So normally most of the aircraft, the thrust vector is slightly pointed upward. Depending upon the design, it may be 2 degrees, 3 degrees or the 4 degrees. So on a normal flight, you do not feel this downward couple because it is being compensated by the thrust. So that is the basic reason whenever you open the thrust in any aircraft or a power in any aircraft, we have a tendency to pitch up the nose. That is the very fact that the thrust vector is pointing upward. So even though the CG is forward, because of this thrust vector, there will be a balance and your aircraft will fly normally. But if you consider in the second diagram here, let us assume that the CG has shifted way too forward. So on this particular case, the thrust vector will no longer be able to compensate the downward motion force by the CG. So there will be always a residual force which points the nose downward. So which I do not want it to happen. So therefore what will a pilot do? A pilot will pull the stick back, okay, so that this downward motion is no more existing, or he will trim back the aircraft. So while trimming back the aircraft, look at the tail portion of the aircraft. This is a tail plane and this is the elevator. Whenever I pull the stick, the elevator goes up, which pushes the tail plane down. So there is an added couple here in the tail of the aircraft which pushes my tail down because of my elevator movement. So we can say that the aircraft is having a virtual weight which is in addition to the actual weight of the aircraft. So therefore, the total weight, that is the actual weight plus the virtual weight combined together, will be more than the actual weight of the aircraft. As we have discussed earlier, if the weight of the aircraft is more, the stalling speed is going to be more. So therefore, sorry, my V2 will be increasing for a forward CG. So now, my primary aim was to reach V2 by 35 feet. In order to reach the V2 by 35, the pilot must initiate a certain action, okay, just before the reaching the V2, or in order to reach the V2 by 35 feet. So what is that action? I need to rotate the aircraft at a particular speed and at the prescribed rate of rotation, which is prescribed by the company. Then only I will be able to reach the V2 at 35 feet, exactly at the end of the takeoff distance available. So therefore, if we talked about it, okay, that VR is nothing but an offshoot from your V2. And the VR is nothing but the calibrated airspeed at which the pilot initiates the rotation sequence by pulling back the control column, raising the nose of the aircraft to its takeoff altitude. So my VR will be primarily dependent upon my V2. And also, if I rotate a particular aircraft at a particular speed, at a particular rate of rotation, the aircraft will finally get airborne when the lift becomes equal to the weight of the aircraft. That particular aircraft, when the lift becomes equal to the weight of the aircraft and the aircraft leaves the ground, that particular speed is known as the VLOF. So coming back to the VR, so the VR has to be at least equal to or higher than the 1.05% of the VMCA, which is set by the regulators. And when we talk about the VLOF, okay, it is the speed at which the aircraft leaves the ground. So this is the place where my tire, the tire of the aircraft, is at its maximum. The moment it leaves the ground, the tire will start retarding. So this particular VLOF will be governed by the maximum tire speed, that is known as the V tire. So my VLOF can never exceed the V tire, which is defined by the manufacturer of the tire. So if I have to talk about this VLOF, there should be a minimum VLOF also. Okay, this minimum VLOF will be governed by the VMU. What is VMU? That is the minimum speed at which the aircraft can get airborne. Okay, this VMU can be determined for all engines operational. Okay, that is VLOF, all engines operational. Here the word N is written in the bracket. My VLOF should be at least equal to or higher than 110% of my VMU, minimum unstick speed, with all engines operating under the EASA rule. And my VLOF, minimum unstick speed, should be at least higher than 105% of the VMU with one engine failure. As far as the FAA or the FAR is concerned, my VLOF has to be at least greater than equal to 110% of my VMU with all engines operational and 105% of the VMU with one engine operational. But however, for the geometrically limited aircraft, so what does a geometrically limited aircraft means? So at that particular VLOF, the tail of the aircraft will touch the ground. So that is the geometrically limited aircraft. So for the geometrically limited aircraft, the minimum V2 has to be at least equal to or higher than 108% of my VMU under all engines operational under EASA rules, and the 104% of the minimum unstick speed with one engine failure. Whereas for the FAR or FAA rules, okay, it should be at least higher than 108% of the VMU and the 105% of the VMU with single engine. So if you want to understand more about the minimum unstick speed or the VMU, okay, it is tested during the test flight. Okay, the VMU is the calibrated airspeed at and above which the aeroplane can safely lift off the ground and continue the takeoff. So during the trial, at a particular speed, the captain of the aircraft puts the nose upward, okay, and the aircraft tail will touch. The tail has got a special modification, the skid is fitted, and finally the speed at which the aircraft gets airborne, that particular speed is nothing but your minimum unstick speed. So now coming back to the V1 once again, as we all have seen that V1 is the maximum speed, okay, at which the captain of the aircraft, if rejects the takeoff, should be able to stop the aircraft before the takeoff distance available. And if he continues the takeoff, okay, he should be able to reach V2 by 35 feet at the end of the takeoff distance available. So how is this V1 related to? Okay, so whenever we talk about the aircraft speeds, takeoff speed, V1 and the VR are always spoken to in conjunction. Okay, like V1 VR ratio, V1 VR ratio, this you have heard it. So my V1 has to be within a certain range from my VR. Let's have a look that. So so by how much? So my V1 can never exceed my VR. So that means to say that I cannot reject my takeoff once I initiate the takeoff sequence. At the same time, my V1 can never be below 0.84 times of my VR. So as I say that, we can also conclude that my V1 is like as if it's been bounded to my VR with a stretchable rubber band. It can collapse and will be equal to my VR, and it can stretch up to a maximum of 0.84 times of my VR. So now what is happening here is that, okay, my V2 has decided my VR, and from the VR, the VLOF has been achieved, and since my V1 again has to be correlated or has to be in conjunction with my VR, the V1 is again, you can say that it's an offshoot from the VR, which is in turn an offshoot from my V2. So out of these speeds, what we have talked about, these speeds can be classified as the certified speed. Whenever we talk about the certified speed, the VS1G or the stalling speed has to be certified. It is certified speed. VMCG again is a certified speed. VMCA, VMU, VMBE and the V tire are all certified speeds. And the speeds we have talked about, that is the V1, VR, VLOF and the V2 are classified as the operating speeds. Moving on further, so if we have to see whatever I have spoken so far, that my VMCG, okay, has to be the list, because when I talk about the V1 is achieved, okay, after 1 second from my V engine failure. So I consider that I have lost one engine during my takeoff. In order to recognize that engine failure, 1 second of time has been given, and after 1 second I will have a particular speed at which I can reject my takeoff and stop before ASDA. That particular speed is the V1 or the decision speed. And if I continue the takeoff, I should be able to reach the V2 by 35 feet. So my V1 on the lower side will be decided by the, that is 0.84 times of my VR, and has to be at least higher than the V engine failure or equal to the V engine failure. And in turn, my V engine failure has to be higher than the minimum control speed on the ground. If I consider the continuation of the takeoff, the captain of the aircraft has to be able to maintain the has to be able to control the aircraft, isn't it? So that is what we have defined earlier. So therefore, in order to control the aircraft onto the runway, my engine failure speed has to be higher than the velocity minimum control onto the ground. So this is a summary of the speeds. So my V2, I have to reach the V2 by 35 feet. In order to reach the V2 by 35 feet, the captain of the aircraft needs to rotate the aircraft. If he rotates correctly, I will be getting the airborne at the VLOF, which has to be lesser than the V tire. Kindly follow my mouse. And also, if I talk about the V1 and the VR, V1 has to be equal to or lesser than the VR. By how much lesser? Up to 0.84 times. Since at this moment of time, the captain of the aircraft has to reject the takeoff. In case if we consider the rejection of takeoff, he needs to apply the brake. So therefore, V1 can never exceed my VMBE. Okay. In turn, my V1 has to be higher than the V engine failure or equal to the V engine failure, because there is a separation of 1 second between them. So, and also I cannot choose an engine failure speed which is below my VMCG, because in order to continue the takeoff, I need some controllability, so the speed has to be higher than the VMCA. As far as the VR is concerned, as we have discussed earlier, okay, it has to be 1.05% of the VMCA, and similarly, as far as the VLOF is concerned, it has to be higher than the minimum on stick speed by 1.08 times or 1.04 times, okay, depending upon whether the aircraft is a geometrically limited or unlimited. Why I have written this figure is basically most of the transport aircraft are geometrically limited aircraft. So now, during the course of my class, you would have been able to find out the answer. What is the range of a V2 with respect to the stalling speed? If we talk about the conventional stall, this is my minimum V2 has to be from 1.2 times of the stalling speed up to 1.25, 1.35, 1.4, depending upon the aircraft which you are flying. And if I talk about the VS1G, it has to be a minimum of 1.13 times the VS1G. As far as the V1 is concerned, with respect to the VR, it has to be between 0.84 times of my VR up to 1 times of my VR. And if my CG is forward, we have seen that my V2 was increasing as the stalling speed was increasing. And maximum speed of the VLOF will be governed by the V tire. So VLOF can never exceed the V tire. And can the V1 be lower than the V engine failure? No. Okay, because there is 1 second of time which is given between the V engine failure and the V1, and the maximum speed of V1 will be governed by your VR, because it can never exceed the VR. And also at the same time, if you have to reject the takeoff, you have to apply the brake, so therefore it has to be less than or equal to the VMPE. So with this, I will be ending the class today. Thank you for your attention. I request you to please subscribe and press the notification icon so that you get the notification for any latest update, and press the like button and share it to your friends, and also give a comment on how I have conducted the class, or if you want any specific topic to be covered in my next class, you can send it onto the comment box. Thank you very much. Have a nice day. Bye-bye.